Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the generation of water vapor. We all know the water vapor can be generated by water heating process under constant pressure for engineering application. In a container with constant pressure, the process of the water vapor generation can be described as: start with compressed water and continuous heat addition. The state of the water will change to State 2. The water is in the saturated liquid state. State 3. The water is in the saturated liquid water mixture state. State 4. The water is in the saturated vapor state. State 5. The water is in the superheated vapor state. The heating process includes 3 stages: preheat, vaporization, and superheat. The heating process of water at constant pressure can be shown in the TV diagram. Firstly, let's talk about the PV and TS diagrams of the vaporization process of water heating under constant pressure. 2 vaporization process of water heating under constant pressure are shown in figures 6.4 and 6.5, the PV and TS diagrams. Noticeable characteristics in the diagrams include 1 point, 2 lines, 3 regions, and 5 states. 1 point. There is a point called critical point on each diagram. 2 lines. There are 2 lines on each diagram, that is, the saturated liquid line CA1 and the saturated vapor line CA2. 3 regions. There are 3 regions on each diagram, that is, the liquid, the saturated liquid vapor, and the vapor regions. 5 states. Water can be at one of the 5 states on each diagram, that is, the state A, at which the water is the compressed water, the state B, at which the water is the saturated water, the state C, at which the water is the saturated liquid vapor mixture, the state D, at which the water is the saturated vapor, and the state E, at which the water is the superheated vapor. We must keep in mind that all the working fluids have the water-like properties. There are 1 point, 2 lines, 3 regions, and 5 states in the PV, TS, and even HS diagrams. Now, let's talk about the saturated liquid vapor mixture. During a evaporation process, a substance exists as part liquid and part vapor. That is, it is a mixture of saturated liquid and saturated vapor as shown in the figure. To analyze this mixture properly, we need to know the proportions of the liquid and vapor phases in the mixture. This is done by defining a new property called the quantity X as the ratio of the mass of vapor to the total mass of the mixture. Quantity has significance for saturated mixtures only. It has no meaning in the compressed liquid or superheated vapor regions. Its value is between 0 and 1. The quantity of a system that consists of saturated liquid is 0, and the quantity of a system consisting of saturated vapor is 1. Note that the properties of the saturated liquid are the same whether it exists alone or in a mixture with saturated vapor. During the evaporation process, only the amount of saturated liquid changes, not its properties. The same can be said about a saturated vapor. In saturated mixtures, quantity can serve as one of the two independent intensive properties needed to describe a state. A saturated mixture can be treated as a combination of two subsystems, the saturated liquid and the saturated vapor. However, the amount of mass for each phase is usually not known. Therefore, it is often more convenient to imagine that the two phases are mixed well, forming a homogeneous mixture. Then, the properties of this mixture will simply be the average properties of the saturated liquid-vapor mixture under consideration. The properties of the saturated liquid-vapor mixture can be determined by the quantity of the mixture and the corresponding properties of the saturated liquid and the saturated vapor. Quantity is related to the horizontal distance on PV and TV diagrams. The properties of the saturated liquid-vapor mixture, V, U, H, and S, can be determined by the relations. Finally, let's talk about the properties of water and water vapor. The properties of water and water vapor include P, V, T, H, S, U, etc., where H, S, U often need to be determined by their changes. The properties can be looked through the tables. The tables are organized with the reference state and reference values. The values of U, H, and S cannot be measured directly, and they are calculated from measurable properties using the relations between properties. However, those relations give the changes in properties, not the values of properties and specified states. Therefore, we need to choose a convenient reference state and assign a value of 0 for a convenient property or properties at that state. The reference state for water is 0.01 degrees centigrade, and for R134A is minus 40 degrees centigrade in tables. Some properties may have negative values as a result of the reference state chosen. Sometimes different tables list different values for some properties at the same state as a result of using a different reference state. However, in thermodynamics, we are concerned with the changes in properties, and the reference state chosen is of low consequence in calculations. Okay, that's all for this task. Thank you very much, and see you next time.